So in the previous classes, we studied about the circuit design style we started. So that will be like the circuit will be performance and the power dissipation will be depends on the large and the circuit design only. So there's two different styles will be there. The one is operating the circuit, the logic circuit that is without clock. The second one is the clocked logic circuit. So initially we started with the non-clocked logic circuit. The non-clocked logic circuit has various different types of non-logic circuit is there. The first one is nothing but the fully complementary logic. This is simple. I can say it is a CMOS logic, complete complementary logic. Next we studied about the Nmos logic. Next we studied pseudo Nmos logic. Then we have to study about the differential cascade voltage switch, that is a DCVS. Then we have to study the pass transistor logic. The first thing is initially the fully complementary logic. The fully complementary logic, already we studied how to implement this fully complementary logic like CMOS. Then we studied what will be the advantages when you use the fully CMOS, then how many number of transistors are required. Those things also we might have seen. Some more examples also we seen to implement the fully CMOS structure, as like this is the equation we given, we implemented that. Then we given some work also like two input XOR gate and some of the two complex logic gate. Then Nmos logic. So in the Nmos logic actually two different types of Nmos logic will be there. One is we can implement with the enhancement Nmos logic. The another one is depletion type Nmos logic you can have. So here in static CMOS circuits, how many number of transistors are required? Totally 2n transistors are required. At the same time, in the fully complementary logic, the area will be more. Why the area is more? Because the number of transistors, how much you need to design for PMOS, the same amount of transistors required for NMOS also. So it's like area will be more. So now when you go for NMOS logic, we are having two different. As I mentioned, the enhancement type, the general circuitry is this. Like the top one will be act as, this one will be act as load actually, right? This will be load, this will be driver actually. So always the load is nothing but load enhancement load transistor they will call. Enhancement type, normally the gate will be connected to VDD. Depletion type. So depletion type, so the gate will be connected to here, is connected to this terminal. Then followed by here we are having the Nmos network, or sometimes we may call this as a pull down network also. Right? So here the set of inputs will give. So how many transistors are required here? When I go for enhancement type or depletion type, the total number of transistors required is n plus 1 transistors are required. N plus 1 transistors are required, but it has a higher power dissipation. Why high power dissipation means, even though if you are not applying the input, the load transistor is always on. So see here we said, see, we implemented two input NAND gates. So this will be your enhancement transistor, because the gate is connected to VDD. So this transistor will be always, it will be on. If this transistor is always on, in the sense, what will be amount? There is a huge amount of the power is dissipating over there. That is why you can say with the help of this, so the power dissipation is very high, we can say. The next thing is here, if we see the depletion region, you see the depletion region here. So here what will happen? That is a, even this also always on actually. So what we can do in the sense, if because it is always on, the second thing is it will be like there will be a problem with the body effect also. To avoid this some problem, so what we did, we have to replace the NMOS by the PMOS. That only the circuit is called as pseudo NMOS logic circuit. That is like a ratioed logic, I can say. That's a ratioed logic. So pseudo NMOS logic. So the pseudo NMOS logic is called as ratioed logic. Ratioed logic means you can able to make scaling with respect to the aspect ratio, in the sense W and L. W by L, that will be, we can make it ratios. Then it will be uses the P transistor as load. So now here the PMOS we used, so this PMOS will connected to the VSS, even this also always it will be on. When this transistor will be turned on, like this is VSS, right? So for PMOS, as you know that your threshold voltage is negative, that already we know. For PMOS, VTP is negative. For NMOS, the VTN is positive. Right? At this already we know that. Now the NMOS network will implement the circuitry in the Nmos network here, keeping that. So what you need to keep low noise margin as high. Then here the resistance of the load, which is the load here, the PMOS, right? The resistance of the load will be very high and the resistance of the pull down network always. So that is why we said it is like if this is 2:1, then this will be 4:1. So always the PMOS network W by L will be twice than the Nmos network. So thing is, if we use that, we can reduce the complexity of the logic. Then we'll have the lower capacitance and it will be speed is fast. But in the Nmos logic, the VTH will be changes due to the body effect in Nmos, because always in the Nmos the substrate must be connected to lower potential. Always the substrate must be connected to lower potential. Means I can say it is zero. Lower potential means simple, I can say zero actually. So the pseudo Nmos is better. So like the load device will not affected by the body effect. The load device will not affect by body effect. Only thing is the driver only will affect. So how we can eliminate only I said. So for Nmos we need to connect the bulb to so this is Nmos, right? So this will be your Nmos, this is PMOS, right? So to avoid the body effect, for Nmos the bulb has to be connected to lower potential VSS. For PMOS also connected to VDD. So the ratio style is better than the switcher to larger fan-in gates. For example, for NOR gate. Why for NOR gate? In the sense, while you are implementing in the NMOS base structure, the NOR gate only will be in parallel structure. So for parallel, the large will have. So at that kind, actually, we can have some better ratio style when you are using parallel type of gates. So the each input will be connected to a single transistor, so that will present a smaller role to the preceding gate. So even we see the example, you can see the 4 input NOR. Here the only thing is simple, I can say here the static current will be always flow. Why? Because as I mentioned here, because like in the kind of NOR structure, when I go for a NOR structure, so what happen in the driver, if any one transistor also if it is on, then automatically there is be a direct current flow path between VDD and VSS. So there will be static current will be there always for with this type of structures. So until this we see in the previous class. So now what we will do, let us continue with that. That is the next non-clocked logic circuit is differential, cascade, voltage, switch logic. That is by short they are called as DCVS logic. Okay. Now what you do? Before enter into this, let us draw the general structure of this. Okay. Let us draw the general structure of this. So the general structure will be the pull-up network is nothing but 2 PMOS will be there. Then here we have the pull down network 1. Then here we'll have the pull down network 2. So these two will be connected to VSS. Then this will be connected to VDD. Then the connection will be like this. It will be like this one. Then this side. So here we are going to take the complementary output, non-complementary output. Both we are going to take. So here we'll take it as out. This side we'll take it as out bar. Now you may think here pull down network, pull down network. So here pull down network is a function. Like example, if I want to say the function, it is a function. This network 2 means it's a function bar network. This is a TCS logic. So here what and all the benefits will get with the help of this, in the sense like so this will provide a differential output signal is available. Differential output signal is available. The very important thing is here it's we don't need to implement another one more circuit for non-complementary circuit here. So both signals output we are getting, like out bar we are getting, right? So this logic family will eliminates the static power dissipation. Which will eliminate the static power dissipation that is present in the ratio logic. Okay, now how many number of transistors are required to implement this? Totally this is 2, PMOS is 2 is required. Here how many N transistor? Even here also N transistor. So total 2N plus 2 transistors required. Here total number of transistors 2N plus 2. Okay, so here the one more thing is, if I want to say in DCVS it has like it has speeds. The circuit is very speed actually in the logic step. Now you can see as I said earlier, the pull down network 1 and the pull down network 2 here, as I mentioned here. So that will be implemented with the complementary function of like out bar. That is why I mentioned it's a function f. This is the function b f bar actually. Since the logic style as this one, because of complementary of this, it has the larger area, correct? Because similarly here the transistor 3 means here also we are having so total 2N plus 2 transistors are required. So example, if the input is equal to 4 means then totally 10 transistors are required to implement this kind of transistor, this kind of logic actually. It has larger area and larger switch capacitance also will be there. So very important thing, what will be the advantage I can say here, like a simple I can say this pull down networks, which will sometimes it may share the some logic and it will reduce the area also, but the complementary outputs will help, the complementary output will helps a complementary output which help eliminate the inverters actually. Because if I going to implement the CMOS logic for AND gate, first you need to implement NAND gate, then you need to add a one inverter to get AND, right? So here, so just straight away we are eliminating the inverter. So this is, so now what we'll do, let us implement a function. Okay, so first example, let us go for the example. So implement two input NAND gate. So if I implement NAND gate, even I will get AND gate output also using DCVS logic. So like these questions only we'll get in the examination. Okay, let us start to draw the structure. First, the top, what will happen? You will have the PMOS. Here also one PMOS, right? Okay. Here bottom, as I said here, this is the function of normal function. So for AND gate, actually what is that? F bar, right? So sorry, function F, or I can say output Y. Output Y will be is equal to A dot B the whole bar actually. So now the complementary function we have to do this side. This is the complementary function. This is not complementary function. As you know that, let us draw the function Y. This is Y. This is Y bar, as I mentioned, right? The function. So this side is Y, right side is Y bar. So Y bar will be A dot B the whole bar. This will become as A plus B. So now you got, right? This one is A bar dot B bar. So now what I will do, let me implement. The first thing is where I should implement here. The implementation is series in connection. Series in connection, correct? No? Then here parallel in connection actually. So now these two will be connected to VSS. Then this will be connected to VDD. Then we need to connect this here. This will be your out bar, right? It is Y bar, I can say. Then this will be your yes. So this will be a Y. Now it is A, B. This is A bar, B bar. So now we can see this here. What is the operation? We can say first consider the operation. How we can perform the operation? If A equal to B equal to 0 means what will happen? You won't get any output because A 0, B 0, both the transistor will be in open switch only. We won't get anything. So the output also will be 0. A equal to 0 and B equal to 0. Right? Then A bar, this is this is A bar plus B bar, right? Because we are applying the De Morgan's law. Y bar is equal to this. So Y is equal to A bar plus B bar. the y bar is equal to a plus b. A is equal to b is equal to 1. When I apply a is equal to b is equal to 1, what will happen? This is also 1, this is also 1. Now what will happen? This transistor will be on, this transistor is on. Now initially you should think this here it is completely charged. Initially it was charged. So 1 in the sense what I'll get? It will be discharged completely. Then I will get y will be is equal to 0 I will get. If I am getting y is equal to 0, then automatically what will happen? It will go to this transistor. Okay, it goes to this transistor, the PMOS transistor will be on. If the PMOS transistor is on, automatically what will happen? The VDD will flow over there. Then here there will be a capacitor because A is equal to 1, B is equal to 1. So this will be bar, right? So this is both are 0. It's an open switch. What will happen? This VDD will come full charge your capacitors. So I will get the Y bar is equal to 1 I will get. You see that? When A and B is equal to 1, then Y is equal to 0 I am getting, because this is the NAND gate, correct? No? This is a NAND gate. Then at the same time you can get CC, I am getting the output as the complementary output 1 I am getting when both are 0. See, A bar is 0, B bar is 0. So this is what, in this way only you need to implement the circuit. So keep it in your mind always. So this will be a, this side is y function, means it is like a b y function, this will be y bar function. Okay, so you always think about whatever the equation they given, so they will give the equation as like a y is equal to a plus b bar. Say example, if I give the y is equal to a plus b the whole bar, now what you will do? If I give in this way, then the y side we have to give parallel. Okay, this side it has come parallel, this side it has to come, y bar will become a series in connection actually. Okay, so now your work is, you need to implement, take as assignment or work. So implement y is equal to a plus b the whole bar. Then the second is y is equal to ab plus c the whole bar. Then y is equal to ab plus c into d plus e the whole bar. This all are considered as assignment for the homeworks. Implement using DVSA logic. Okay, next I'll go for pass transistor logic. Okay, so the pass transistor logic is nothing but we are going to study about the behavior of pass transistor. Behavior of the pass transistor. In the sense we are having two pass transistors, Nmos and PMOS transistors. We need to have the behavior, how it will behave. So before that what I will do, let me tell something over there, like we are having for Nmos. For Nmos, see, this is the Nmos, okay. Always like when I am going to give the input, you consider this is either source or drain, anything you can take. The gate will be applied to VDD. Now here I am going to give input. here we are going to take the output. Okay, so now let me say when I give VDD here, the example I will take VDD is how much? 5 volt. Now what about the threshold voltage? So as you know that how to calculate threshold voltage, VTH is equal to 0.2 times of VDD. Then it will be 0.2 into VDD is 5 volt. Then this will be 1 volt. The threshold voltage is 1 volt now. Okay. Now the Vout. The Vout will be the Vout will be range 0 to VDD minus VTHN. The range of Vout will be what? 0 to VDD minus VTHN, because the transistor slowly, when you vary from 0, the transistor will be turned on. But when the transistor will be turned on, as it reaches the threshold voltage, then it will be turned on. Means it's losses. So VDD minus VT voltage. So I can say here the Vout will be is equal to the range of output will be 0 to VDD is 5 minus 4. Totally it is a 4 volt. The range is this only. Okay, this is the input. When I give input is equal to 0, what I will get? When I give the input range will be how much actually? The range of input will be from, we can give anything, but I am giving up to 5 volt actually. But the output range will be 0 to 4 volt only. So let me see here. When I give Vin is equal to 0, this is Vin, this is Vout table. Okay, I'll put. When Vin is equal to 0 volt, when I give Vin is equal to 0, what will happen? The transistor is on, so Vout also I will get 0 volt only. The 0 is 0. Next, when I give 1 volt, I will get 1 volt. Next, when I give 2 volt, I will get 2 volt. When I give 3 volt, I will get 3 out. When I give 4, I will get 4. When I give 5. When I give 5, what is the voltage I will get? The output will be degraded with the threshold voltage. Means the output will be degraded due to threshold voltage. Even I will get 4 only. Even when you apply 6 also, I will get 4 only. So it will be maintained 4. So that is why I said here, you can see when I apply 0, I am getting the output as 0. But when I apply 5, I am getting the output as 4. So that is why I can say it is a good in 0, right? While passing the good 0, passing good, but weak in 1, because of 5 volt in digitally if I say it is 1. So on, for that only I will say the characteristics of Nmos transistor will be so passing good in 0, passing good in zeros, but weak in 1. So that is about the Nmos. So for PMOS will be in the reverse. So it will be good in 1, then weak in 0. So now simple I can say the pass transistor. What I will do, I will take another example. One transistor is there, right? I am going to take another one more transistor. You think like this. This is VDD. This is also VDD. Okay. Now this will be your Vin. This will be your Vout. Now we can say this portion. It's nothing but node. It should be something like. Now you can see when I give, what will be the VA will get? What is the maximum voltage will get VA? Any idea? VA the maximum. VA max will get from 0 to VDD minus VTH. Okay. Now what about Vout? Not a 0 actually. I'll say is instead of a 0, let me change this to V in actually. Okay. V in comma VD minus VTH, because whatever the V in, same thing I'll get. Correct? So V in. Next here, what about this? VA comma VDD minus VTH. So the range of Vout also will be VA to VD minus VTH. Now let me apply the value. I will apply Vn is equal to 2. When I apply Vn is equal to 2 volt, what will be your VA? VA also I'll get 2 only. Why? Because so the maximum here I can get up to 4. 4 up to 4 volt will be able to allow. So the VA also will be 2 only. And here the maximum how much will be 4, right? The maximum of VA is 4 volt. Maximum Vout also is 4 volt. So I will get 2 volt. Okay. Now let me check 5 volt. What about the 5 volt now? If I give 5 volt, the VA I will get as 4 volt only. But what about the Vout here? I will get 4 volt only. So when you are connecting the pass transistor or in series in connection, there will not be no effect, or there will not be no effect if you do cascade in connection. Yes, I hope you might have got it. But this is the case 1, correct? This is the case 1. Let me go for case 2. Like this is the one transistor, this is nothing but your VDD, but this one is driving this. This will be your Vout. Now you think this will be your Vin. This is also the another Vin. Now you tell me what is this VA I will get, what is the Vout I will get. Yes, I need the answer. So, come on. Tell me the answer. What is the value I'll get it for VA? Then what is the value we'll get it for Vout? How much value we'll get? Or you can tell what is the maximum value we'll get it. Chandu? Chandu? Parnita? Yeah, tell me. How much you'll get? What is the VA will get? What is the Vout will get? Just give me the answer. Ishwar? Jivisha? Yes, Ishwar. Jivisha? Karthik? How much the VA is required, how much the VA will get in the sense, the range of VA will be from V into VDD minus VTH you will get. So that is your VA actually. Now what about your Vout will get? The Vout will get in the range of VA minus VTH actually. So VA minus VTH in the sense, because this voltage VA is nothing but what is the maximum output I'll get, VDD minus VTH. So I can say it is nothing but the VA is nothing but the range will be from V into the Vout will be from V into VA minus VTH. So VA is nothing but VDD minus VTH minus VTH. Then I will get the ranges from, will get the output of VDD minus 2 VTH. You can see here the maximum voltage how much you will get here, VDD minus 2 VH. Okay, the same example we can take, the VDD is equal to plus 5 volt. Then what about your threshold voltage? Then the threshold voltage will be a 1 volt, correct? So now I will say when Vn is equal to 2 volt, the Vn is 2 volt, this Vn is 2 volt, then this Vn also 2 volt. Example. Now what happened? The VA will get the maximum voltage of up to 4 I will get, means up to 4 how much you give the input, the same thing I'll get in the output. That is what meaning. So VA will be Vin. Okay, so if I want to write still better condition will be Vout is equal to Vin for Vout is equal to VA is less than or equal to 4, or I can say VDD minus VTH, general formula I can say. Simple, right? Vout is equal to Vin for VA is less than or equal to VDD minus VTH. It won't go for negative value. Next you can see how much it is the VA value now. VA also 2 volt only. Okay, now you think the VA is 2. Okay, now here VTH is same only, it is 1 volt. What is the maximum voltage I will get? It is 2 minus 1, VA minus VTH, correct now? VA minus VTH. So it is nothing but how much? It is 1 volt. The maximum I will get 1 volt only. But my input is 2 volt. So the output will be 1 volt. Now we'll take example here as 5 volt. The input is 5 volt I will take. If the input is 5 volt, what about the VA I will get? VA I will get as 4 volt only, because the maximum is 4 volt only. So here input is 2 volt only, here remains same. Okay, the input is remains same here, 2 volt only. Now what happened? 4 volt minus the threshold voltage 1 volt. So like the maximum is 3 volt here, I can able to get. So I will get the output as 2 volt. What are the input 2 volt I can, same thing I will get. So that is why I can say when the pass transistor, if any one pass transistor is driving the another pass transistor, then the output will be degraded. So this is not the good style to make the connection or to make the circuits. In this way you should not do. I hope you might have understood that. So for you, exercise, one exercise, take this diagram, you can do it yourself. This is VDD. This is VDD. This is also VDD. Now this will be your V in. This is also your V in. This is also your V in. This will be your V out. You can take this portion is nothing but your VA. This is VB. This will be your VC. This is VD. Okay. My question is find the V out for the following Vn. Vn is equal to 0 volt, 1.3 volt, 2.7 volt, 3.8 volt, 4.5 volt, then 5 volt. So for this you need to find out the output voltage V out. Note down the question. So the parameter are not given. So if the VDD value is not given in the question, by default you can choose 5 volt. Sometimes they may give VDD, VTH is not given. Then you know the formula for to find the VTH. You have to apply that formula and you have to find out the VTH. Okay, now what we will do? So let us implement all our other circuits for pass transistor logic. So you can use the pass transistor logic networks to implement different logic functions you can implement. So simply I can say the pass transistor logic uses pass transistors network to implement different logic function. So with the help of the pass transistor network, we are going to implement different logic functions. So here combinations of AND, that is pass transistor, arch switches in series. Switches in series connection. Then this will be a AND gate in the pass. Then when the switch is in parallel connection, so OR. OR gate structure. Okay, so even you can implement some different functional network also. So in the sense simple, I can say series and AND gate, series AND gate in the sense. So let me put the examples here. Okay, see, pass transistor. Now two input, right? This is I'll say example is AND gate. Two input AND gate. This is, I will take it as A. Sorry, this is not that. So let me go for an example. So like a combination of AND and OR, the pass transistor or switches in series implement and the function, and the pass transistors are switching the parallel contribution. So that is AND realization, then that will be a OR realization, the switch will be in OR, right? This is not accurate because let me implement and show. Okay. So now let us implement and gate. Now you can see before to implement this, I'll put a simple idea for you. I will get see example. One pass transistor I'll take. Okay. Okay, this is one pass transistor. Now this will be, this is your A example. Okay, this is A. This will be because the input always you have to think about in this way. When the pass transistor goes, this will be your input, the gate will be the control. Okay, so sometimes you may call the gate always is a control signal. The source, I can say source or drain, anything, because when I go for pass transistor I can consider anything. So but the better always when you are getting when you are giving the input is 0, then at that time that will be at the source. When I am going to give a higher value, then that will be drain, but no need to worry about that. The source and drain here, this is the control signal, this is Y, I can say Y. Now you can see here, this will be a, this is A example. Okay, this is A, this is something called as X, you take it as X. Okay, this is A. Now what is Y? Y is equal to A into X. Y means example, F X is equal to 0, then what is A? Y is equal to 0. Correct, no? if x is equal to not x, because control signal you have to say this is control signal. A is a control signal. Okay, A is a control signal. So you can see x is equal to 0 means y will be 0 irrespective of the if the A is not 1, or I can say if A is equal to 1, example, or I'll say A equal to 0. First control signal, because always you have to check for control signal. So leave about this, okay? Yes. If A is equal to 0, then what is y? Y will be 0. If A is equal to 0, y will be 0 irrespective of x. If A is equal to 1, then y will be is equal to 0. This is what I mean to say. I hope you got it right. So now in the pass transistor, this is the gate always will be controlled. G is a control signal. This will control, the gate will be get controlled. Then X is nothing but your input. Always. See now, let us implement the AND gate here same the way. So for AND gate actually, the truth table. Let me go for the truth table for AND gate. A, B, then Y. 0, 0, 0, 1, 1, 0, 1, 1. Then it will be 0, 0, 0, 1. My see, this is input. Okay. This is input. This will be your output. But here one you can give as a input, the another one you can keep as a control. Correct? Both no need of input actually. One is the input, the other one is the control. Here you can say which is we can keep as the input, which you can keep as the control here. You can say here what I will do, the A I will keep as example. Anything you can keep as control. So I will make it A is control. Example, A is control. Then I will say the B is A is a control, the B is a input. Okay, so now you can say this is the one form of the gate I am saying, PAB. Now when I go for this and again, so now you can say control is A, this is A, B is nothing but your input. Now this will be your Y. Okay, now Y is equal to, now you apply A is equal to 0, control signals, you can see here. A is equal to 0. When I apply A is equal to 0, what will happen? Y will be 0 because of open switch, Y will be equal to 0 only. So we got irrespective of the B value, even B is 0 or B is 1. Next, I will apply A is equal to 1. When I apply A is equal to 1, this transistor will be turned on. When the transistor is turned on, what will get? The Y I will get as B. So if the B is 0 means, say example A is 1, B is 0, what will get? 0 1 will get. If A is 1 but the B is 1, then Y will be is equal to 1 I will get. See, one single transistor is enough to implement actually. But we can implement in some other way also. Like the fast transistor will have the advantage of being to be very fast, and the complex gates can be implemented with the minimum number of transistors actually here. So here the one more thing, the same thing I cannot implement in this way. Okay, so now what we need to do, let us go for the proper circuit actually, pass transistor and gate. Pass transistor logic style circuit. Then circuit, say example, the one more circuit is given here. See, this is B, this is A, this is B bar, this will be a buffer. Okay, this is buffer actually, this is a buffer. So here is the output, A, this is B. So input A, B, and the B is controlled, because here I cannot say, here you can see in this truth table one is input, one gate I said, but both are input, A and B, both are input. Even you can do in this way, see here, both are input A and B, then B is a control signal. So when you apply, so even this also I will get, like B is a control signal in the sense you consider B is equal to 0. If B is equal to 0, if I make this is 0 means then this will become as 1. If this is 1 in the sense, this will be your open circuit, this will be a closed circuit, then I will get as B. Output is B I will get. So in the sense, irrespective of if any one input is 0 in the AND gate, output will be 0 only, correct? No? So B is 0 actually. So I will get B only I will get. So similarly you can implement. So now, as I mentioned already, it is good. So now like how you can implement the complex, the complementary pass transistor logic. Complementary pass transistor logic. That is they will call us by short CPL. So here let us implement and both I will get in the pass trans logic, both and XOR and XNOR. Okay, so now what we will do, so let us implement AND gate or NAND gate, both the function we have to get PMOS and NMOS. So now it's very simple to implement. Okay, so here complementary logic in the sense, so simple I can say complementary logic means it's a kind of transmission gate also I can say, or two I can say like both NMOS also I can say. Let me implement for first AND and the NAND. Okay, so for AND and NAND, if I say that transistors or switches will be in the parallel connection just before only AC, correct? So now how we make in the sense, so which is the control signal? B we are taken as control signal, so B and B bar. So what I will do, the control signal I make like this. This is one, this is one example, right? This will be a B, this will be a B bar setup. Okay, so now first, what is the NAND gate actually? It is so the structure will be like this. This is B, then we'll have this, this will be this. So this I will get as A, B. This is your A bar, this will be your B. The complementary logic. So how you can get, this is AND gate actually. Output I'll get as YB. So this is at input your output, that is Y I can see. See here control signals. You can see this is the control signal gate. Okay, this is the gate. Color I drawn because as you know the gate is polysilicon. Just for a simple namesake, I am drawn in this way. next this is your A bar. This is AB bar. This is AB. See, with the same control signal, we implemented the complementary logic. This is for your AND gate. This is your NAND gate. See, you can apply the inputs and you can check. Like a control signal B bar, when you apply the B value is equal to 1 when you apply. So this transistor will be on. When you apply B is equal to 1, this will be on and this will be on. So example, I will make it as a transistor T1, T2, this is T1, this is T2, this is T3, this is T4. So now I will say AB, right? A is equal to 0 and B is equal to 1. For this, what is the output we'll see first. So what and all will on and we to off. B is equal to 1 in the sense, then what about B bar? B bar will be 0. So B is 1 and B bar is 0. So B is 1 in the sense that transistor, that T1 and T3 is on, the T2 and T4 is off. So now automatically what will happen, if T1 is on in the sense, then what is the output I will get? The output will be Y is equal to A bar I will get. So what is the A bar? A is equal to 0 means is equal to 1. Then what about this I am getting here in the bottom? T2 and T4. So like T3 also is on. So if the T3 is on in the sense like the same, the one more output is, the output will be what? Y will be is equal to what I will get here now. This is on, right? If this is on in the sense, I will get a bar only even. Same, see? Correct, no? So it is nothing but A is equal to 0 means 1. So I will get as both the places 1 I will get. This is complementary way of getting. So this is the AND logic I said. AND means we will get the NAND only will get, correct, no? Because when you are going to implement in the CMOS, no? Actually in the CMOS logic structure only what will happen when I am going to implement NAND will get. This is a complementary. Complementary in the sense like I am having a Nmos actually. If you are having a CMOS over here, then the situation will be different. So that is why the name has come complementary. So the output will be complementary. So when I give 0 and 1, the realization is done as AND gate. But it's not AND, it's a NAND gate output. So I'll get the output as 1 when I'm going for parallel structure. Similarly, we have to do for XOR and XNOR also. So you know how to implement this if you are getting the if you are having the confusion over there in the sense. Let me write here the expression here. What we'll get here? We'll get as A bar dot B. What about here? We'll get B dot B bar. Then this is the parallel, right? Then I will get A bar dot B plus B into B bar. A bar dot B, this will be B dot B bar, then I add arrow. So B bar is 1 I will get, or the B will be common. So A bar plus B bar. Okay. When I use this kind of circuits here, we will have the load capacitance will be there. Okay, Then we can use this for suitable for adders and the multipliers actually. So the main advantage of this design styles will be like for while differential output signals are available here also. So this differential output will eliminate the inverter and can make design fast actually. So this logic family will reduce the internal capacitance. It will reduce the internal capacitance. Reduce the internal capacitance, and it is useful for suitable for power efficient implementation. Power efficient implementation is a thing is, if I want to say the power delay product of complementary pass transistor logic is about 10% better than the standard CMOS logic. The power delay product of CPL, okay, is about 10% better than standard CMOS. Standard CMOS logic. So when I go for XOR or XNOR logic. XNOR logic. So similarly, even here also. So see, this will be your B bar. This will be your B. Now we'll apply the input here. It is a bar, B, and here it is A bar, then B. Sorry, not A bar and B. That is A bar, then this will be A bar, A. Then we have this as like this. This will be your A exclusive or B. This will be a exclusive or B. So this is your XOR. This function is XNOR function. It will give the output. These are the two examples about the complementary pass transistor logic. The complementary output. So like here, doesn't require the inverter also, even here also in the output logic. This is about the non-clocked. Okay. Next, let us see about the clocked logic family. Next is clock logic family. Clock logic family, in the sense the problem is that previously what will happen? like any one of the transistor will be on. So many advantages and disadvantages we have seen in the non-clocked logic. Now in this large or in this clocked logic family, we'll discuss it will usually faster than the static logic families. Static family logic family lessons which we discussed the previous one. Next thing is here, the performance usually comes at expense of high power dissipation. So first let us discuss the domino logic family. Then the second logic family that we are going to call the differential current. So now what and all we are going to study. The first one is we are going to study the domino logic family. The second one which are going to study the family is called differential current switch logic. By this short I can say DCSL. DCSL. So this both has the better power delay product than the domino circuits due to the low internal node voltage swing, and it may have the possibility of larger panning logic gates. So these two we are going to see in the clocked logic family. The first one, let us see domino logic, or sometimes domino CMOS logic also you can see. Domino logic. Now domino logic, if I have the clock logic family, if I say it will work based on two operation. In the sense two operation, the sense one is like two transistor will be the one is the pre-charge transistor. The second one is evaluation transistor. Or I can say pre-charge phase and the evaluation phase. So these two phases will be there for clocked logic family. So in the sense here totally when you are going to use this kind of clocked logic family circuits, so we can avoid the static power dissipation. Completely we can avoid the short circuit power dissipation, that is it won't come. Then we can avoid the leakage power dissipation also when you go for this. First thing is let us go for the example of domino logic. Example, like what is it? Implement two input domino NAND gate. So before that implementing, I will show the general circuitry of domino logic. General circuit, okay. So the general circuit will be look like this. VSS, that will be your V reading. Now we can see clock, or sometimes we may call as phi. Okay, now you can see here Nmos, that is pull down network. So, or I can say preferably Nmos Logic circuits. Still the diagram is not yet over. Output, I will connect here one inverter. So this is static CMOS inverter. So now we can have this one output here. You can see this. I will take this Q. This V, right? This will be like your Q bar. Actually, it is the output, or I can say this output is actually supposed to be V out bar. Actually, then this is V out. Okay. Let me say this will work. How the operation is. The operation will be like this. When you are applying the clock signal, this is the clock signal, right? When I go into clock signal, this will be a pre-charge. This will be your evaluation phase. So during the evaluation phase only it will produce the output. During the pre-charge phase, nothing will happen even though you give the inputs. So this will be your inputs. Okay. So here, this is simple. I can say it is a weak PMOS or very small but PMOS. Then I will name it as, that is M1. This is M2. This is transistor is M3. Okay, we'll make it as like this. Now, first case, what will do? This is general structure. No, what I will do here, I will implement a 2-input NAND gate now. So I'm going to implement NAND gate. So for that NAND gate, let me go for diagram. So Nmos network 1, 2, both are in series connection. Then here we should have one more lower this, right? Then this will be your clock signal. So this is the PMOS. Then this will be your VDD. This is your VSS. Then the output from here we have to connect a one static CMOS inverter. Then this will be your V out. If this is the V out, you should think always here we will have the one load capacitance will be there. Then we'll have the load capacitance, internal load capacitance. Here also we'll have the internal load capacitance C1, C2. Then I will say this is A, this is B. And this will be your weak PMOS, as I mentioned. Okay. Now you can see, you might have seen CMOS Domino Logic. The CMOS Domino Logic, if we see how many earlier in the classes we studied, how many transistors was required for Domino CMOS Logic? For Domino CMOS Logic, or CMOS Dynamic Logic, not dynamic, okay? CMOS Dynamic Logic. For CMOS Dynamic Logic, how many transistors was required? Like 2 plus n transistors were required. But here, for Domino Logic, how many transistors are required here totally? You can see 1, 2, this is M1, right? M1, M2, this is your M3, then I can say this is your N1, this is your N2. This is your static. Okay, this is the static CMOS inverter. Static CMOS inverter. Now you can say 1, 2, 3 here plus 2, 5 will be there, correct? 5. So total I can say how much is required? 5 plus N transistors are required. And I'm going to implement the circuit in Domino Logic circuit. Okay, so now you can see here first operation. How we can do the operation here? Let us go for operation during pre-charge. During pre-charge, in the sense, what will happen? Like the case 1, okay? Or clock is equal to 0. During pre-charge, in the sense, when the clock is equal to 0, it will be in the pre-charge. So I can say this portion, the top one, this is both are the M1, M2 are called as M1, M2 are called as pre-charge transistor. This is M3 is called as evaluation transistor. Okay. Now, when clock is equal to 0, what will happen? M1 and M2 will be, so M2 is always on. So make a note. Right? M2 is always on actually. So M2 is always on in the sense there will be like a small. So it's a very weak PMOS actually. Very small amount of current will flow. Like a small current will flow actually in this place, right? M1. So M1, M2 will be is equal to on. When the M1 is equal to on in the sense AB irrespective of the input, and I can say M3. M3 is off. When M3 is off, what will happen? So there will be a chances like VDD will go over there. Then we are having the one more capacitance here. You can see here. Okay, this is also one more capacitance, load capacitance, internal capacitance you can say. So this capacitance will be charged. So how much it will be charged? This will be charged from VDD minus VTH completely will be charged. So total amount. So VDD will be charged fully over there. When there is a static CMOS over there, then automatically what will happen? When this goes, it's completely like it will be charged 1, then there is a chances of this will get a discharge, right? Because initially all the transistors, so initially the CL dash I can say CL dash is pre-charged. Okay, so that will be discharged, then I will get as 0. You can see here the output is 1, here the output will be 0 we are getting. So initially, so when clock is equal to 0, it is in the pre-charge mode. It is in the pre-charge mode. Now what we are going to do? We are going to apply the inputs now. So we are going to apply the inputs in the sense during evaluation phase. During the evaluation phase only the circuit will work. So during evaluation phase means when it will be in the evaluation phase. So like a clock is equal to 1. If the clock is equal to 1 in the sense like a M1 is off, right? No, then M2 is on only. It is permanently on. Okay, fine. So but it is a weak, very weak PMOS I can say. Then what about M3? M3 is on actually. When the M3 is on, so now irrespective of input, what I will do, A, B, I will apply 0, 0. When I apply A and B is 0, 0, both are open circuit. When both are open circuit, what will happen? Initially this was pre-charged already, right? So I will have 1, then it will be 0. So let me say A, B, this portion is nothing but, what is this portion? I will say this portion is something called as X. Okay, so this portion I will say that is X, then output is Vy. So 0, 0, what is X? X will be 1, what will be Vout? Vout will be 0. Next I will give 0, 1. What will happen? 0, 1. So I will give 0 and 1. So this will be open, this is on. Again what will happen? Remain same, Vout will be 0 only. Again 1, 0. What will happen? 1, 0 means, so 1, 0 in the sense this will be on, right? This is 1, this will be 0, this will be on. The N1 transistor is on, N2 transistor is off. What will happen? This will try to discharge, right? Try to discharge actually here because of load capacitance, but the good amount of before is get try to discharges. So what will happen? The value will go over there, so it will be charged. Even this also will get discharges. So how much will get here? I won't have VD minus VTH because this will be, the charge will be shared to this also. So but logically if I say I will have 1 over there, X will be 1. What about Vout? Vout will be 0 only will get. Next, when both are 1. When both are 1, what will happen? Both are on. When both are on, this will be completely discharged. When completely discharges, the X I will get as 0. When this is 1, 0, then automatically this is an inverter, right? So this will get as Vout is equal to 1. See here, this is nothing but your Domino CMOS logic. Very important thing about this in the, so why you may have the question as like, why we need to keep the PMOS as weaker? Why weaker PMOS or weak PMOS? Why weak PMOS? It will helps to keep the output logic at 1 for that purpose only. Because you can see, if it is very weak, if I keep, always it will be on in the sense this transistor X position always will try to keep as 1 only. Why? Because when I am having the series of transistors over there, this will try to discharge completely. If keep us discharges, automatically what will happen? We won't get the output properly. So due to this transistor, it continually it will maintain the value of VD minus VTH in the transistor. For that reason only we are using this the weaker PMOS actually. That is the smaller CMOS. Then very important thing is here. Then one more thing here. So this domino circuits can implement only non-inverting circuits. Very important, because always it will produce the non-inverting output only, non-inverting circuits. So it is not easy to use the domino design style actually, because only for non-inverting circuit only we can use. So then next thing is this domino design style is better suited for large fanning gates. Large fan gates such as NOR, because the each input will be connected to a single transistor, so it will present a smaller load to the preceding gate, so it is possible to achieve the high performance. So next here we see the output of the gate is sometimes it will be pre-charged only to discharge in the evaluation phase, so that we can say the signal activity will be in the output. the signal activity will be output can be high. It is not a scalable. As standard CMOS due to low noise immunity. Compared to standard CMOS circuits. So this is about the Domino CMOS logic. So advantage, and you need to explain about the operation. So even the question may ask so like this, okay? So sometimes you can ask assignment or homework exercise, you can say. Exercise, implement the following functions using Domino Logic. The first one is y is equal to a plus b. Second is y is equal to a into b plus c. Then third is y is equal to a b plus c into d plus e. So you need to implement this. So keep it in your mind whatever the exercises I am given over there, because in the examination or in the test it may ask anytime. Not only this Boolean expression, any kind of Boolean expression. This is example I am given. So this is all about the today's class. So in the next class we'll study about the next logic, that is differential current switch logic. That is one of the very important logic in the clocked design state.